Fine. So this session is about one of the important uh, model of generative AI, and I think the previous session taken by Dr. Satyendra must have given you overview of generative AI. So now it's time to delve into more technical details uh, of different type of generative AI models. One of the model is variational autoencoder, and in later in this course we will study different types of generative models like generative adversarial networks, then diffusion models, LLMs. So to start with, this will be the brief agenda. uh, will just give you an idea about what exactly is generative modeling. I'm sure you must have gone through these concepts of supervised and unsupervised machine learning, also the concept of generative modeling. But for better understanding of the participants, I'll just quickly summarize these concepts again, and then we will move forward to the techniques such as autoencoders, then variational encoders, and we will see the applications of variational encoder. And in the next session, which is practical session of variational autoencoder, we'll do experiments and we will implement variational autoencoder again on that MNIST data set. I'm sure yesterday everybody was able to implement the CNN experiment. We have also shared the notebook on CNN on the canvas. You can access that. I request all of you, I advise all of you to please religiously follow these experiments. Then only you will be able to grasp these concepts, because understanding the theoretical part is altogether a different story. However, the practical implementation gives you more insights how these models work, how you can visualize the data, what are the dimensions at each of the layer, and what type of input you provide to these models, what type of output you get from these models. So I advise all of you to please implement all the notebooks which are given to you. It's best that you implement them during the session itself. Even if you are not able to do that, do it as a homework after the sessions. So now, starting here, supervised and unsupervised machine learning. I think you must have heard this term multiple times in last 2 days. Again, giving you a brief overview. So in supervised learning type of setup, we have the data X and the corresponding label Y. So if it is a classification problem, image classification problem, image will be your data input X, and the label cat in this example will be Y. And in supervised machine learning, your goal, main goal or objective of learning is to find a function, to learn a function which can map the input data to your label Y. Suppose you are building a classification model which can classify between cat and dogs. So your mathematical function or supervised machine learning function or the model should have a mechanism of mapping these images to a corresponding label. One of the typical or most popular example is classification, where you are classifying an image to a particular class or category. Another example, specifically in the field of computer vision, could be the object detection. So in image classification, you are just classifying the whole image to a certain category. However, in the case of object detection, you are detecting different objects in the image. Not only detecting, you are localizing them, you are drawing a bounding box around them and assigning a class to them. So that is object detection. Third type of supervised machine learning could be semantic segmentation. So In contrast to the object detection where we have a bounding box, here you are classifying each of the pixel. You are assigning category to each of the pixel in the image. So here we have a clear boundary of each of the object in this image, that is semantic segmentation. Another example could be image captioning. So in image classification, you had labels as class of the image, cat, dog. However, in image captioning, the label is a particular sentence which is describing the image. So there is involvement of natural language processing as well here. Now coming to unsupervised learning, which is our main focus here, because your generative models belongs to this category. So here in unsupervised learning kind of setup, we have unlabeled training data. We don't have labels, just the data. And here our goal is to find the underlying hidden structure of the data, to find the pattern among inside the data. One of the typical example of unsupervised machine learning could be clustering. In clustering, what do? We group, we find similar kind of data, and then we group them together in clusters. And the criteria for finding these groups, formulating these groups, is the common kind of structure which is there in the data. I hope my voice is clear. There was some issues yesterday. I mean, the issues were reported by various participants that there is some issue in the voice. I hope the voice is clear now. If there is no, sir, it is clear now. Yes, sir, now it is clear. Fine. So I'm receiving mostly yes. Still, if you find any issues with voice, then please let me know. Write in the chat. We can find a solution. I think there was some issue with the microphone. The microphone was little distant from me. That is the reason you are receiving very low voice. Now, coming to other examples, like this was one of the example of unsupervised machine learning clustering. You can see these data points are clustered together based on similarity somewhere in the underlying structure. Now, another example of this unsupervised learning could be dimensionality reduction. In this example, you can see here, we are converting a three-dimensional data to a two-dimensional data. Now, our whole this problem is related to finding the excesses along which there is a major variation in the data. So converting this 3D to 2D means there will be one dimension where there is not much of the variation in the data. So we can remove that particular dimension and only consider the dimensions where we have higher variations in the data so that it can clearly define the data points. So this is another type of unsupervised machine learning. We call it dimensionality reduction. One of the popular technique for dimensionality reduction is principal component analysis. Now, another example of unsupervised learning is autoencoders. We will have detailed discussion related to autoencoders in the subsequent slides. But I just want to give you an example here that yes, autoencoders are also one of the type of unsupervised machine learning, and this autoencoders are popular for feature learning. We can learn a latent representation or a compact representation of the input data. Thus, we can learn features of the input data. In supervised learning, if you have seen yesterday in different sessions, in CNN, we can extract. CNN is mainly for representation learning. you can extract features with the help of CNN. So that was supervised machine learning, where uh, the output at the fully connected layer can be used as features, and you can use any of the classifier to train to use these features for classification purpose. Now here in unsupervised learning, we can also learn features, and autoencoder is one of the example of learning features in unsupervised fashion. So the idea here is without having any external labels, we are learning the feature representation from the input data. Now, next example of unsupervised machine learning is density as estimation, where we want to estimate the distribution, the density distribution of the underlying data. In this example here, we have two examples. First one is 1D estimation. we, I'm sorry. In the first example here, what we are trying, we are fitting a Gaussian into this density. And in the second example, where we have two-dimensional data, here also we are trying to estimate the density of this input data. We want to model the density. We want to fit a model in such a way that the density will be higher where we have more number of data points. And here you can see that example, the graphical example here. Wherever we have more number of points, the density will be more. Now, why we are more focused on unsupervised machine? Before that, just a summary of supervised and unsupervised learning. In supervised learning, we have labels, and the goal is to learn a function for mapping between the input data X and the label. And there are different examples here. However, in the case of unsupervised learning, we don't have any label. And the main goal is to learn some kind of hidden patterns or underlying structure inside the data. Uh, uh, it could be clustering, it could be dimensionality reduction, it could be density estimation. Fine. Now, why we are more concerned? Why we are talking too much about this unsupervised machine learning? Why what could be the reason? So this question is for the audience. Please tell me why we are focused on unsupervised learning here. Why we are putting so much emphasis on unsupervised machine learning. You can write your answers on the chat box. Why we are focusing more on unsupervised machine learning? What is the advantage we have with unsupervised learning? To find patterns in the input data? No, that is just the definition of unsupervised machine learning. But why we are focusing more on for predictions? No burden of labeling data. Correctly answered, Bharat. Thanks. So the main advantage, the main advantage of unsupervised learning is we need not to label data, and we have abundance of unlabeled data with us. So labeling the data is very typical. That's why we are focusing here on unsupervised learning, and the training data is very cheap here. Why cheap? Because we don't use labels, and we are able to learn from this lot of data available with us. Imagine where we have to label the large volume of data. It's very typical one. So that's why we are more concerned about unsupervised machine learning. And still, in previous decades, the more focus of machine learning researchers was towards supervised machine learning, whether it is proposal of these convolutional neural networks, deep learning based methods in last 1 decade or so, or 2 decades, the more focus was towards supervised machine learning. But now, with these terms, generative AI, we are uh, putting our efforts towards unsupervised learning models, and that is doing wonders these days. There are n number of open problems if we deal with unsupervised learning, and it's definitely an active area of research. Now, coming to generative models, I think you must have gone through the details related to these generative models, but just for the simplicity, I want to highlight it again here. In for generative models, what is our goal? Our goal is to take the input training samples from some distribution and learn a model that represents that particular distribution so that we can generate new data which follows that input distribution. So basically, we have training data generated from some distribution P data. These input samples, which are training data, and these training data follows a distribution P data. And from this, we want to learn a model. We want to learn a model which is P model. And what's the condition here? This P model is very similar to this P data. So that's the whole objective of these generative models. So basically, these generative models can address the density estimation problem. In density estimation problem, what we were trying to do, we were trying to estimate the underlying distribution of your training data. And that was our main goal in unsupervised machine learning kind of setup. Fine, I hope the basics are clear. We can do a lot with these generative models. We can generate realistic samples. We can create, we can do super resolution with given edges kind of images. We can do colorization. There are a lot of applications which we can do with the help of these generative models. And also, like training these generative models can also help us in finding the latent representation, and these latent representations can be used as general features for other supervised tasks as well. Fine. Now, coming to one of the model, one of the technique, which is called as autoencoder. I'm really sorry. Coming to one of the popular model, I'm not saying this is a generative model. This is, but yes, this frames the base of one of the popular generative model, which is variational autoencoder, which is variation of autoencoders. So autoencoders means they are combination of encoder and decoder kind of structure. As we have seen earlier, encoders, these autoencoders are good in dimensionality reduction. They basically they are unsupervised machine learning approach. They helps us in learning a lower dimensional feature representation from the unlabeled input data or the training data. So basically, autoencoders, dimensionality reduction. You can see here we have input data X. Let me have the marker here. Yeah, fine. So we have high dimensional input data X, the encoder structure, which will generate a lower dimensional feature representation Z from this unlabeled training data X. So basically, this helps us in dimensionality reduction. This helps us in learning features. This helps us in data compression. Fine. Now, why this z is smaller than x? That means it will reduce the dimension. But why we need a dimensionality reduction here? Why do we need a dimensionality reduction here? Why can't we use this input data directly? This question for the audience. So whenever we are talking about dimensionality reduction, that means we are trying to find out a compact representation of the input data. As we have seen earlier in principal component analysis, we are removing the data excesses or dimensions which have very low or negligible variations. So that are not helping us in discriminating the input data. We are only considering the dimensions. We are only considering the dimensions or the excesses in which we have maximum variations. I have got one answer from the chat that reducing the computational complexity. Yes, definitely. More the dimensions in the features, we need more computations. So that is one of the advantages of dimensionality reduction. But the main purpose here is to remove the redundant dimension, which is not helping us in any of the tasks. Now, uh, uh, in autoencoders were proposed 2-3 decades back. Originally, the of course this is neural network based model. So originally we used linear layers plus some kind of activation functions here. Later, after proposals of deep neural networks, we used deep neural networks and fully connected layers. And after the advent of CNN or popularity of CNN and ReLU activation function, the encoders started using the combination of CNN and ReLU. Now, of course, I just answered your query. Why dimensionality reduction? We want features to capture meaningful factors of variation in the data. We are only considering the excesses which have maximum variation in the data. Fine. So what do you get here? As an encoder, you take X as the input, and then you get Z, which is of lower dimension. So that's the output of the encoder. Now, what do we want? What does this decoder do? And how do we find out? How do we train this encoder? How do we learn these feature representations? So basically, what do? We take these features which are produced by this encoder based on the input data. Then we use decoder as a second network which will be able to output X cap, which is the estimation of the input data. So basically, we are giving X as input to the encoder. This encoder is giving us a latent representation or a smaller dimension representation Z. And from this Z, using this decoder network, we are reconstructing the input itself. So this X cap is the reconstructed input. So basically, we are training this encoder and decoder to reconstruct this input. And in between this process, we are finding this Z, which is a feature, lower dimensional feature representation of this input data. So basically train such that features can be used to reconstruct the original data. We also call it auto-encoding or encoding itself. Now this decoder can also have a similar structure that of the encoder. So the process is going to be, in this process, we are providing the input data. We pass through the input data through the encoder first, which could be a convolutional neural network. Let's say we have a 4-layer convolutional neural network. And then we get features here. Try to recall our discussion on convolutional neural network and the later layers which were helping us, which was helping us in extraction of the features. So you can assume this kind of network similar to the CNN. We can use a 4-layer convolutional neural network in the encoder part. So basically this Z is giving us the feature representation, which is output of the CNN at the fully connected layer or output at the convolution layer. Now, in decoder network, we can again use 4-layer convolutional network, which gives you the reconstructed version of this input data. So in this whole process, we train these two networks, encoder and decoder, and by reconstructing the same input with the help of these features, we basically train an encoder which gives us a compact representation of the input data. And how do we do this? So just to give you a summary here, you can see this example here. Again, the same MNIST kind of setup. There are 784 neurons. We are bringing it down to 20 units, which is a feature vector. And then we are reconstructing this input of the same dimension 784. But in this process of reconstruction, we are basically learning the feature representation in a lower dimensional space from this encoder network. So autoencoder is a feed-forward neural network, or we can use other type of deep neural network. And its job is to take X as input and predict X. Very simple one. Take X as input, bring X as output. This X should be similar to the input X. Now, in this process, learn abstract features in an unsupervised way, so you can apply them to a supervised task. Now, what you can do, once you have learned these features, you can use them in any of the supervised tasks. Fine. This is another representation of it. Here we have encoder. This is latent space, lower dimensional representation of the input data, and then the decoder reconstructs the data back. Now, how do we achieve this? You have a d-dimensional input X. This encoder function V projects this d-dimensional input to k-dimensional plane. We call it features. And this is basically the dimensionality reduction. And then the decoder network, the decoder function U basically projects again the k-dimensional feature space to d-dimensional xcat. So basically the overall output, this xcat, will be U applied over V of X, which is nothing but a linear function. Now, how do we learn? How do we train this network? So what we have to do, we have to learn these U and V matrices, which are weights. And how do we train this? What could be the loss function here? As you are aware, if we are going to train any of the network, we need to formulate a loss function. We have to minimize that loss function by adjusting the weights in the network or parameters in the network. Sorry. So the loss function here could be the L2 norm between the output and the input. So basically the whole idea of training is to minimize this L to learn U and V, the weights in this U and V. That is how we also call it L2 loss or L2 norm. Now, this is another kind of depiction here. Trains us that features can be used to reconstruct original data. We have to minimize this L2 loss function. Now, what exactly we have to do is we have to what we have to do what we have to achieve in the reconstructed data is my pixel values. If I am considering an image data, my pixel values in the reconstructed input should be same as my input pixel images. I mean input pixel data in the image. Now the whole idea here is you don't have any label, but still what you are achieving the feature representation. So once we have trained this model, we can throw away this decoder network. We can throw away this decoder network, and what we are going to do with this feature representation, this we can use for any of the supervised tasks. This encoder can give me a feature representation of the input data. And then once I have extracted these features, I can use these features to train any of the classifier and use it in a supervised manner. So basically, this encoder can be used to initialize a supervised model. So now what we can do here is we can provide the input data to the encoder, extract features, and then initialize any of the classifier which can be which is a supervised kind of model. Fine. So that was one of the utilization here. So basically, we have unlabeled training data from which we can learn good or general feature representation, and then we can utilize these feature representation to initialize any of the supervised learning problem where we don't have much of the data, where we don't have enough amount of data to train the classifiers, where we have only small data. So what we have seen here is these autoencoders are able to reconstruct data and are able to learn features which can be further used for supervised models. And these features are basically able to capture the factors of variation in the training data. Now, what are the limitations? So basically, to summarize, autoencoders can reconstruct the data and can learn features to initialize any of the supervised model that we have seen. These features capture the factors of variation in the training data. But the question arises here, can we generate new images? Can we generate new images from an autoencoder? So basically, these autoencoders are not generative models. They do not define any density distribution, any probability distribution. So that's the problem with autoencoders. Limitations, yes. No probabilistic interpretation. The latent space, the feature representation space is deterministic and doesn't model any kind of uncertainty or the randomness. Then there is a poor sampling ability, can't generate new data. no control over the latent space structure. The latent representation can be discontinuous and non-smooth. So basically, autoencoders are not generative models, but yes, they frames a base of another model which is generative in nature, that is variational autoencoder. So in autoencoders, if we want to generate new or realistic or diverse samples, we need a better structure for the latent space, which is given by the variational autoencoder. Let me give you a brief overview of this, how graphically I'll explain this. So this, let's say an autoencoder model is trained on a large data set of faces. And suppose the encoding dimension, the feature dimension, the latent space dimension is of 6. So suppose I'm developing a model for reading this face, and this facial image is encoded in latent attributes, which is of dimension 6. So basically, we are attempting to describe this observation in some compressed representation of dimension 6. We have, with the help of this encoder, what we have done, we have described this image in terms of the latent attributes, and these latent attributes have a single value. Like for smile here, we are using 0.99, which is a single value. You can consider the normalized range from 0 to 1. Similarly, for skin tone, let's say the single value is 0.85. Fine. But this is the limitation of the autoencoder. Instead of having a single discrete value in the latent space, we prefer to represent each of the latent attribute as a range of possible values, or maybe sample it from a probability distribution. So here, let's take the example of Mona Lisa here. And what could be uh, what value you will assign to the smile attribute to this particular image? This is 0 here. But if we have a flexibility to sample the value of these latent attributes from a distribution, we'll have a flexibility. We can have a generative approach here. So basically, the limitation of autoencoder, there is no probabilistic interpretation. The latent space is deterministic. Deterministic means one value for particular latent attribute. We cannot model any kind of randomness or any kind of variation in any of the latent attribute. And that restricts us to generate new data. We'll see in the subsequent slides. See here. Now, with the help of variational autoencoder, in contrast to autoencoders, we can represent the latent attributes for a given input as a probability distribution that you can see here. And once we have encoded this information in the latent space with the help of probability distribution, while decoding this latent state, we can randomly sample the values of the latent variable or attribute from this distribution. So now you can see here, there are two examples of decoder here where they have sampled the values of these latent attributes from this distribution, and they are quite similar with each other. So the idea is the values which are nearby to one another in this latent space will correspond with similar kind of reconstructions, right? You can see here for each of the latent attribute, the values are sampled from the distributions and they are close by. And you can see the decoded output is very close by because they are sampled from this nearby, sampled from the same distribution. So these points are nearby. I hope this is clear. So that's the basic difference between autoencoder and the variational autoencoders. Fine. So I think there were some questions related to this one. How do we label the data for supervised models? Now, my point here is instead of labeling the whole large training data, which is unlabeled for us, what we can do is we can do a small set of, we can label a small set of features rather than labeling this whole data. Since we are computing compact representation, very accurate representation of this input data, we have learned this representation. Now we can use a very small data or small data, labeled data for training this classifier. So that's how it is helping us in supervised learning. I hope the question is clear. Fine. So let's look from another perspective. The same example here, the MNIST data example. You have seen this kind of setup where you are giving input to the encoder as dimension 784. This is being represented as dimension uh, uh, of 20 in the feature space or the latent space. And then finally decoder is decoding it into the original shape, reconstructing it to the original shape. So basically, you reduce this 784 pixel uh, image to a 20-dimensional using a normal autoencoder or variational autoencoder. Now, this normal encoder part is giving you 20-dimensional mean value or just the center of the cluster. And so when you decode or you reconstruct or your decoder try to reproduce that input data, it will be the same sample near that mean. However, in the case of variational autoencoder, it will give you the variance along with the mean as well. So basically, what you can do with this mean and variance, you can generate some sample which you have not seen earlier because of the variance available to you. And still it will be very similar to the input image cluster. So that's the advantage. That's the basic concept of variational autoencoder. And that's the difference in comparison with the autoencoder. This is the graphical representation what we have just talked about. In autoencoders, yes, we revolve around the mean itself. However, in the case of variational autoencoders, we do have mean along with the variance. And then while decoding or reconstructing, we can sample the data from this distribution. With this, I just want to take a 2-minute break and then we will continue our discussion on variational. Okay, so welcome back. Sorry for the interruption. I had to take a small break. Uh, Now coming back to variational autoencoders. Uh, there's some issue in changing the slides. Yeah, fine. So now, instead of in comparison with autoencoders, here we are modeling the probabilistic generation of the data, and these uh, uh, encoders and the decoder network are probabilistic in nature in comparison with the auto encoders. Now, we have already talked about computing Z from X in the encoder network, and then computing X back from Z in the decoder network. So here also, similar to autoencoders, we are going to learn the Z in the latent space representation from the input data X, and from that Z we will reconstruct back the X as the output of the decoder network. So now our encoder network, which is Q of Z given X, X is the input, Z is the feature representation, which will be the output of the encoder network. So we define this encoder network as Q Z given X with the parameter phi, and it will give us two outputs. One is the mean and the covariance of this Z given X. So this will be our direct output of this encoder network. In the case of decoder network, it will be similar one, and it will start with Z as the input, and this decoder network P X given Z means the input is Z and we are computing X. So this decoder network will give us the mean and the covariance of X given Z. And here, the parameter for this decoder network will be different from the encoder network, and this will be theta. Fine. Now, so basically, we will sample from this distributions. Z will be sampled from this distribution QZ given X, and again, in the decoder network, the X will be sampled from this distribution P X given Z. That is the representation here. We will sample this Z from this distribution Z given X, which is defined by this mean and covariance. Similarly, we will sample X given Z from, we will sample X from this distribution X given Z, which is defined by mean and corresponding covariance. So basically, what exactly these two networks are doing, the encoder network and this decoder network, they are basically producing distributions over Z and X. That is what these two encoder and decoder networks are giving, and basically they are giving us an opportunity to sample these outputs from these distributions. I hope this is clear to all of you. Now, this encoder network and this decoder network, they are doing different tasks here. So what we can, in other words, what we can say is this encoder is, we can say this encoder is a recognition or an inference network. However, this decoder is the generation network. Why so? Because this decoder is generating new data from this latent representation Z. However, this encoder network is giving us a feature representation for which can be further utilized for recognition or inference. Fine. So this decoder network, we are mainly concerned here with this decoder network, which is capable of generating new data. However, in the case of autoencoders, we were more concerned about this encoder network because it was giving us some feature representation which was helpful for training any of the supervised models. So this is the generation network. This decoder network is the generation network. So this is the summary here. In traditional autoencoders, we learn to compress the input data in a lower dimensional space, and we reconstruct the data with the help of decoder. But the problems were they were not generative in the nature, and the latent space was not smooth. We were only considering the value, mean value there. There was no distribution. The distribution was not learned by the autoencoders. However, the variational autoencoder is fixing the problems associated with autoencoder. The encoder outputs a distribution, not just a single point. Similarly for the decoder. So basically, your variational autoencoder is a generative model which learns the distribution over the input data, and it consists these parts. One is the encoder, whose task is to map the input data to a probability distribution here. Secondly, the decoder will reconstruct the data from the sampled latent variables. So encoder will give you a probability distribution in the latent space. In the decoder, the latent variables will be sampled from this probability distribution generated by encoder, and then it will be reconstructed back. Right? So basically, we can say that variational autoencoder gives us smooth and continuous and structured latent space, which in turn gives us the generative capability of the data. Now let's see how we achieve this, how a variational autoencoder will help us in generating this data. There is a bit of mathematics involved, but I'm not going much into detail of this mathematics because um, yeah, I have a question. What are the advantages of using variational autoencoders in place of autoencoders? So the answer is very simple. The autoencoders don't have the generative capability. However, the variational autoencoders have that generative capability. And why VAEs has that generative capability? Because the encoder represents the input data in terms of probability distribution, and we can sample the data from that probability distribution, which gives us the capability of the generative capability. Instead of sampling a single value, a fixed value every time, uh, in variational autoencoder, we have a smooth and continuous structured latent space, which helps us in generating new data. Fine. Now let's suppose there exists some hidden variable Z here. We are talking about the decoder part here. So suppose there exists some kind of hidden variable Z which generates an observation X. Fine. This is the decoder network. How much similar the output will be? Can we be able to quantify? Uh, yes, of course, you can quantify that. Any generated data can be matched with the original data to quantify how similar it is. But that's not the objective here. The objective is different. So let's talk more about how we are going to generate the data. This is the decoder part. Suppose we have a hidden variable Z in the latent space, and this generates the observation X. So this is the reconstruction part here. Now here, what we can see is only the X, but we want to infer the characteristics of Z. This we are talking about the generative, the decoder part. So basically, what we are going, what does the decoder do, the decoder basically learns the distribution here and the distribution of Z. I hope I am audible here. I hope I am audible. Okay, fine. So what uh, we can see here is X, and we might like to infer the characteristics of Z. So in other words, what we want to compute is the probability of Z given X, and with the help of Bayes' theorem, we can compute P given the distribution of Z given X in terms of the distribution X given Z and Pz and Px. But the problem is computing the probability of Px is quite difficult, and that makes it an intractable distribution, and which is the problem with us. So it's not that simple the way it looks. Dealing with these distributions is not that simple. Since we are not able to compute this Px, we cannot infer this particular distribution, and that makes it intractable distribution. What does just for the clarity, I just want to define what is intractability here. That means the integral has no closed form solution. That makes it intractable distribution. It means the integral is computationally intractable. Fine. So that's the problem with us. And now, what is the solution to it? What solution we can have, since this is intractable distribution? So yes, there is a solution. We can apply a variational inference to solve this problem. So basically, what does it mean? We can approximate this intractable distribution by another distribution which is tractable. Since this is intractable distribution, we will take help of other distribution which is tractable in nature. So what we are going to do here, we can define the parameters such that these parameters are very similar, so that we can use them to perform approximate inference of this intractable distribution. Let me give you some more insight into it. So we can, what we are going to approximate here, we are going to approximate P z given x by another distribution Q z given x. We know this distribution Q z given x. So basically what we can do is this Q z given x is a tractable distribution. So what we can do, we can define the parameters of this tractable distribution Q z given x such that they are very similar to the distribution P z given x. And now we can use them to perform the approximate inference of this intractable distribution. And how do we achieve this? We take help of KL divergence. I'm not sure how many of you have studied. I'm just giving you a brief about it. So basically, the KL divergence gives you a metric. This measures the difference between two independent probability distributions. So our aim here is, since we talked about approximating another distribution, which should be similar to the one which is intractable. So basically, we will ensure that this distribution QZ given X is similar to this PZ given X. We can use KL divergence. That means we can minimize this KL divergence between these two distributions, which will signify that these two distributions are very close to each other. And then there is a long mathematical derivation for minimizing this KL divergence term. I'm writing it directly here, which contains two terms. The first term, E log Px given Z minus the KL divergence of Qz given X and Pz. So we are not going to derive this expression, but someone has derived this uh, this derivation. We are directly using it. So here the first term basically represents the reconstruction likelihood. What does it mean? This is the distribution of reconstruction. Z is the latent space representation. X is the output of the decoder network. So basically, decoder network is reconstructing. So this particular term represents the reconstruction likelihood. And the second term, this particular term, ensure that our learned distribution Q Z given X, which is of encoder network, is similar to the true prior distribution P of this latent distribution Z. Fine. Now, what we are going to do here, let's visit this graphical model. You can see here, we have X as input. We are going to infer, we are going to infer this Z, which is latent space representation. So there will be some neural network which is mapping this X to Z. And we can further construct this model into a neural network architecture where we are mapping this Z to X. Fine. So basically, from Z to X, we have this distribution Px given Z, and from X to Z, we have this distribution Qz given X. So we would like to use our observations to understand the hidden variables. This is how it looks like. Now, we will formulate this loss function here, and this loss function has two terms you have seen earlier. And the first term, it is reconstruction likelihood. This helps us in maximizing the reconstruction likelihood. It penalizes, it uh, reduces the reconstruction error. And the second one is your KL divergence term, which encourages our learned distribution, this encoder distribution, QZ given X, to be similar to the true prior distribution PZ. So this is again the summary. The encoder maps the input X to a distribution. Then latent space sample Z from distribution using mu mean and the variance, and then decoder basically reconstructs this input X dash or X cap from this sampled latent vector Z. So basically, the idea here is rather than directly outputting the values for the latent state variables in standard autoencoder, the encoder model of variational autoencoder will output these parameters of these distributions for each dimension of latent space. That is important here. For each dimension of the latent space, the encoder will give you mean and variance. You can see here you have mu1, mu2, or maybe mu n. Similarly, sigma 1, sigma 2, and sigma n. So for each dimension in the latent space, you will get this encoder will give you mean and variance. Fine. And then by using these mean and variance, we have a probability distribution. We will sample from this distribution and reconstruct it with the help of this decoder network. Fine. So this is just the depiction here. You have a data point. Suppose you are generating an image. You have an inference model. We remember we were calling the encoder network as inference model. We get a latent space representation of this, and then there is a generative model, and then we have an objective function for this. Now there is a problem, and the problem is, how do we train the neural networks? Can someone tell me? Question to the audience. How do we train our neural networks? Backpropagation, right? Very simple answer. So, and in backpropagation, what do we calculate? Gradients, right? We differentiate. So basically, our distributions should be differentiable. So what we are doing here is, in variational autoencoder, outputs a distribution. Outputting a distribution means giving the parameters mu and sigma rather than the single vector. And then we, for reconstructing, we sample this Z from this distribution. Right? This is the background. Now, how do we train this? So basically, we use backpropagation, and while training this model, what we have to do, we should be able to calculate the relationship between each of the parameter in the network and the final output loss. That means we need to compute those gradients, right? So calculate the relationship of each parameter in the network with respect to the final output loss. Fine. That is what we do in the backpropagation. We compute the gradients with respect to each of the variable or each of the parameter of the network, or gradient of the final output loss. But that's the problem. This kind of setup is not feasible for random sampling process of parameters. What we are doing here is, we are randomly sampling these parameters from a distribution. That means this sampling is not differentiable. And that's the condition for the backpropagation. For training these neural networks, we need differentiable operations for backpropagation so that we can train. We can change the parameters with the help of those gradients of the loss with respect to these parameters. Now again, there is a problem. So we can take help of an idea called reparameterization trick. I know there is a lot of mathematics here, but you won't believe I have removed a lot of mathematics from here. Try to keep it simple so that just you can give and get an overview of what exactly is happening there. So this reparameterization trick, what we do, we randomly sample eta from a unit Gaussian distribution, and then sift the randomly sampled eta by latent distributions, mean mu, and the variance sigma. Basically, we are scaling this latent distribution. In the diagram itself, you can see here, these are deterministic nodes, mu and sigma. They are fixed values, fine. But this Z have randomness. So to remove that randomness, to make it deterministic so that we can differentiate it, to make it differentiable, what we are doing here is we are adding a new random node here and making this Z as deterministic node. So this eta is a random variable, and we are using this random variable which is sampled from a unit Gaussian. And with introduction of this eta, the whole expression of this Z can be differentiable with respect to mu and Z, the whole expression of the loss function. So now what we can do, we can now optimize the parameters of the distribution, and still we are maintaining that ability to randomly sample from that distribution. So that is called as the reparameterization trick. This is what the depiction of back propagation here. Now, since this is a deterministic node here, now we can do differentiate. We can do differentiation here with respect to each of the parameters. Fine. Now that is just the summary here for variational autoencoders. You have the input data set. This is the X space. In the encoder branch, you compute this distribution. You have a prior distribution, which is important one. Remember, we were computing the KL divergence between these two distributions. Here you have got the Z space, the latent space. From this latent space, you will sample randomly the Z, and this decoder will again produce the reconstructed input. Fine. Now, how we are going? We have trained these variational autoencoders. Now, how we are going to generate the data? So basically, as I told you, in autoencoders, we were only concerned about the encoder since we were capturing the features as output of the encoder. However, in variational autoencoder, we are more concerned about the decoder network, which we can use for generating the data. Now, how we are going to use it? So basically, you can sample this latent representation Z from the distribution, feed it to the decoder network. Decoder network is defined by these means and covariances. Sample this X given Z from this distribution, which was approximated earlier. I have shown you that kind of demonstration. Now let's see how, with the help of this variational autoencoder, we can generate data or samples from the MNIST data. So this decoder network, this decoder network is trained. This decoder network is trained on MNIST data, and these are samples which are on the right hand side. You can see the samples generated by variational autoencoder trained on the MNIST dataset. Now, what do? We represent basically Z is the representation of the input data in the latent space. Now, suppose you have this latent space is of two-dimensional, Z1 and Z2, and you can see here how with the combination of every Z1 and Z2, different values of Z1 and Z2, try to remember, uh, we will have mean and variance for each of the dimension in the latent space. Now, if we vary the values of these two latent attributes, Z1 and Z2, we can vary the shape of these digits. So we can have different dimensions of this latent space. You can have 3-dimension, 4-dimension, or n dimension. Since in specifically in MNIST data set, we have 28 cross 28 image, which we have brought down to this 2-dimensional latent space Z1 and Z2. Now you can see the combination variation in Z1 and Z2 and see the combinations of these digits. This is the visualization of the latent space of MNIST dataset. If you vary those latent attributes, this kind of output you are going to get. Now, this is another application here for the facial images. You can see here let's say Z1 is representing the degree of smile, and Z2 is representing the head pose, whether it is tilted in one direction or another direction. So now, basically, this dimension of this Z can encode various interpretable factors of the variation. Now you can see when we vary this Z1 from up to down, the degree of smile is varying here. However, if you are going to vary this Z2, the tilt of the head is varying. So that is how there is variation on in the data or the data generation part. If it is more nearby the mean of these latent attributes, you will have similar kind of data being generated. So now, basically, these can be, again, this can be a good feature representation. These latent space representation is a good feature representation. Now, if we do the visualization of the latent space, if we compare the auto latent space visualization of autoencoder and variational autoencoder, you can see here it is on the MNIST dataset. You can see how in autoencoder this how these data points in the latent space are distributed. They are not smooth, randomly distributed for each of the digits. In latent space, we are using 2 dimensions here. However, in the case of variational autoencoders, you can see there is a very smooth and continuous distribution for each of the digit here. There are 10 digits, 0 to 9. And for each of the digits, it is smooth and continuous distribution in the latent space. Now, try to remember, try to recall, we had 2 terms in the loss function. One was the reconstruction likelihood part, and another one was the KL divergence part. So if we use any one of them, we won't get very smooth kind of distribution in the latent space. However, if we are including both the terms in the loss function, if there is a combination of them, you can see there is very smooth and continuous distribution of the latent dimension, latent variables for the digits. So basically, if we are only using that reconstruction or reconstruction likelihood, it will our distribution will deviate from the prior to describe some characteristic of the data. If we are only using the so if we are not using the regularization, there will be a problem while learning the distribution. It will be a very small distribution, very small variance in the distribution. And if we use the KL divergence also, so this KL divergence basically ensures we have enough sufficient variance to yield a smooth latent space. So that's why we get this kind of distribution if we use both the reconstruction loss and the KL divergence in the actual output. So now it's time to summarize. Variational autoencoder is basically the probabilistic spin to your traditional autoencoder. It allows us generating data in contrast to autoencoders. It defines the intractable density. And what are the pros? We have a principled approach for generative models, allows inference of this distribution QZX, which can be also useful as a feature representation for any other tasks. One of the limitation, one of the issue with variational autoencoders, we get somehow a blur version or lower quality versions of the images. If we compare the results of variational autoencoder with generative adversarial networks, I hope you are going to study generative adversarial networks in subsequent lectures. So basically, you will see that variational autoencoders, the quality of the generated image is not that good that is generated by the generative adversarial. It is active research area. There's a lot of scope, still scope is available to do research in this. Fine, I think that's time to conclude. I'm sure this was little complex in terms of mathematical equations. If you have any queries, please let me know. I'm happy to answer these questions. Any other question? I think there was one question related to how to compute PZ. So PZ is basically a standard. We follow, we assume a standard normal distribution for this latent variable Z. We are directly following a standard normal distribution for PZ. So if there is no other question, let's break this session. We'll inform you the time for the next practice for the next session, where we will be implementing the variational autoencoder, and we will see how the visualization, how we can generate new images once we train the variational autoencoder. We'll see the visualization as well. Whatever theoretically we have studied, we'll practically implement that. Again, we will be using Colab. Thank you. Let's break for the lunch.